problems. I'm like, oh, these are really good problems for the book, and they were already ones in my lecture slides. With, okay. And then I ended a chapter and I was supposed to write the next one, but I didn't put my lecture slides on my computer. So you know what? All right, whatever. You guys have exam week, so I have a couple extra minutes off from class there. So we'll see how this goes. I don't know. Maybe I'll forget the lectures up here. We'll just have to, I don't know, go wander in circles for an hour. Anyway, be very biblical though, right? Just wander in a circle for 40 minutes, and we'll think about the symbolism behind it. Okay. So, all right. Anyway, so last time we were discussing the behind-the-scenes work for what makes something aromatic, right? And we had kind of went through our criteria of what we need to, what properties we need to have, I guess might be the way of saying it. What's the checklist we have to fulfill for something to be aromatic. Now, why do we care if something is aromatic? Well, there's a couple things to think about here. First of all, like we've mentioned, right, whenever something is aromatic, it is going to have a specific way of reacting and behaving, right? The other way is that there is some inherent, I don't know if inherent's the right word, but maybe it's fine, right? There's some inherent stability that's afforded through the formation of an aromatic system, okay? Aromatic systems are extremely stable, right? And so there's a drive to reform aromaticity. There's a drive to form aromaticity, okay? And here's what I mean. Oh, that's not what I mean. Like I said, it's been one of those days. All right. What am I missing here? No. All right, let's try this the old-fashioned way and just see if it wouldn't let me scroll, so I have to fit the entire lecture on like a little white piece there. Let's see if we get this going here. If not, oh, there it is. Of course, the answer was that he tried restarting it. Okay. Tried turning it on and off again. All right, so back to what I was talking about. If we have this guy here, right? So if we're back out here, make assessment. That's the question, right? So remember what I was talking about before the little technical hiccup there is there's a drive to make an aromatic system if possible, right? So the requirements for an aromatic system is that we have a ring, K, right? Everything has to have a usable p orbital. Well, we've got a bunch of, or not a bunch, we've got some double bonds, right? Okay, those are usable. Now we've got those lone pairs, right? Those lone pairs that are on the oxygen. Now, what we can do basically, or if we want to answer that question of can we make an aromatic system, do we have usable p orbitals, is can we start to draw resonance structures where we move the electrons through the ring, right? That's another way of kind of approaching it, right? So, right, we've got the lone pairs there, right? So one of those lone pairs we can think of as part of the ring itself, right? So we have 2 electrons from the lone pair, and then 4 from the double bonds, which makes the number 6. Is 6 one of our Huckel numbers? Yes, right? So we have a ring, it's got 6 electrons, all those 6 electrons can talk to each other, right? So this is an aromatic system. But remember, behind the scenes, there was this one idea, right, this one check that we can't really account for. And we said this stuff has to be planar, right? Well, what's the geometry here? Well, all the carbons are sp2 and they're planar, but what's the oxygen? sp3, right, and tetrahedral, right? So we may not expect that this would be completely planar. But if that oxygen basically moves itself into the plane with the rest of the pi bonds there, right, then this forms an aromatic ring, which is a stabilizing influence. So there's a cost to move the oxygen into the plane, right, but there's a net gain by making an aromatic system. You guys catching what I'm saying with this here, right? So we just on paper, if we just look at this stuff, we wouldn't expect this all to be planar, but because there's this drive to form aromatic systems, then this actually would be planar. Okay? Yes?
Would this be similar to the nitrogen, like the pyrimidine that we drew, like
Well, sort of, right? One of those lone pairs is involved in the aromatic system. The other one is involved. The other one's orthogonal then. Right?
Okay, so then like you know how it's like the hamburger.
Yep. Yep.
That would be the same thing in this situation?
No, the lone pair is part of the hamburger. One of the lone pairs is.
Okay.
We have to have 6 electrons in there.
Okay.
Good?
Dr. H, can you show us how to draw the resonance for this particular?
Good question. Draw the resonance structures. Oh, I didn't bring my 5 pounds of. Yeah, I'm not going to do it now. I'm not going to learn unless I get sugar. I'm an ant. Careful. Blah, 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 right? And you can keep pushing stuff around through the ring there, right? Now, of course, Right? These aren't great resonance structures. That's not the point, though, is it? The point being what? Can all these electrons start to talk to each other? Can you make a continuous, right, set of, be careful with that. You're not going to have that. Can you have a continuous set of electrons talking to each other, right? That's all it comes down to. Now, what you will notice, and what might be important to pay attention to is, right, the negative charge can end up on certain, right, can end up on certain carbons, and that's going to be important a little bit later, okay? So we'll come back to that idea there. All right. Oh, what the hell? Serious. Dude. Seriously, like I've been using this program for like literally years and this has never happened. It's gotta be today, I don't know. Nothing? Let's see if I swap over to Jen Ken's not gonna help me either. Nothing. Piece of junk. Try this one more time. All right, we'll do this the old-fashioned way here. I know how to fix this. Let's restart every damn thing. All right. So let's see if that'll help it out. In the meantime, right? So in the meantime, while this is going, let me see if I can sufficiently kill time to make it seem, you know, not this is what was all planned to happen, right? Right? But anyway, so with these aromatic systems, not all aromatics are the same, right? So as in the furan that we just drew there, that 5-numbered ring, we noticed that, or what we should start to see is that the way that the atoms can talk to each other is not always equal, right? And so what I mean is that not all aromatics are the same in terms of the strength of their aromaticity, okay? Benzene is kind of the go-to example. It's great, it's nice, it talks to each other, but some things aren't as aromatic as the others, right? And when you start to get to these hetero-containing cyclical systems, that might be something to start to consider. Right now, what does that mean for us practically? Not much, right? It doesn't mean much, but I'm just saying that this isn't necessarily a binary thing. And what I mean is it isn't necessarily aromatic or not, right? There's degrees of how aromatic something is. And if we get to this later on in the semester in the lab, right, then do this for you guys. Let's see, what do we have here? Put my password for you guys to see it. And that down. Time to get an A, the good old-fashioned way. Alright. But anyway, what I was going to say with that is later on this semester we'll do a reaction with an aromatic system that'll behave more like a set of conjugated dienes rather than just an aromatic itself, right? So that's all I mean with it. It's just there's different degrees as we start to make bigger and bigger conjugated systems. That's all it comes down to. Okay. I'm gonna guess this didn't do a damn thing, but we'll see. I got high hopes. Sure, Microsoft Teams has to log me in, you know. I swear I turn this on constantly. Like I said, it's just been a weird day. What can I say? There you go. We can talk to my Brazilian friend in Texas. So how you guys? Where? That? No. It's like you spilled mustard on
I
there or
did
something.
not. It was boiling.
It was blank. I don't know about that. I don't know, maybe. I don't know how it went down there. Maybe it was from my coffee or something like that. I saw the answer just. What the hell? Dude, what the crap? This is so stupid. There's gotta be something else. Don't worry, I'll just restart it every time I need a new blank piece of paper. Anyway, alright, we'll just erase as we go. We're so dumb, so dumb. Okay, yeah, good. Yeah. It should go automatically back and forth, but sure, alright. Whatever, I'm getting sick of this. It's been a day. Anyway, alright, so back to it here. Alright. Okay, make assessment. Glad my misery is entertaining for you. You know how much fun it is to be in front of people and to start bombing because of your equipment, right? So many benzene jokes I got stored up for this. So do we have a ring? Can all the pi bonds talk to each other? Is everything flat? Everything's sp2 hybridized here, right? Nothing mysterious. How many electrons? 10. Is that a Huckel number? Yeah. So is this an aromatic system? Absolutely, right? So notice I didn't say that it has to be all in a ring, right? I say it has to be in a ring. Obviously, as we get to these larger Huckel numbers, then we're going to have polycyclic systems, right? So different fused ring systems together. Now, this is our buddy naphthalene. It's a very common organic reagent. You guys probably know what naphthalene smells like. It's mothballs, right? So this is what that characteristic smell of mothballs is. So who knew, right? But well, actually, you guys did know, right? Because this is aromatic. So all right, never mind. You guys will get that later on, like when the fire alarm goes off. Like, oh, I get it. It's a pun on how smells work. Okay. Alright. There's this. So a bunch of rings. What do we got? 2, 4, 6, 8, 10, 12, 14. Right? So 14. Is that a Huckel number? Yeah. Is this all a ring? Yeah. Can these all talk to each other? Yeah. All right. So this is our buddy anthracene. I don't really know what this one smells like, but another common structure that we see quite often there. But this is another one of these polycyclic systems. Right? Now, what you will notice, actually, you probably won't notice that. Let's see here. Let me try and draw this to the best of my garbage artistic abilities. Okay. We have 2 rings. How many total electrons?
10.
10, right? Are we getting 10? One pair of that nitrogen there, right? So it's 10 a Huckel number. Yep. So this is indole, I-N-D-O-L-E. Again, one of these common things, I guess, more in the pharmaceuticals, right? That kind of thought there. I always forget how to draw this one.
With the NBSP3.
Yeah, technically, but it'd be actually flat later, right? I like that. Just kind of wiggles it back and forth. I don't have it selected properly. It's just time for me to go home. Make the same assessment. That's pretty much the exact same as one that we just saw there. However, this is one of the most important heterocyclic ring systems. Why? Have you guys seen this before? What do they teach in biology these days about DNA?
Oh,
This is a purine ring, and purine rings are I believe it's adenine and, which one is it? Guanine, okay, you guys know better than I do, right? So those are based off of purine systems, right? There's something that's more important than that, right? This is also caffeine is a purine derivative, right? So far more important than what holds you together, right? Well, I think in many ways it holds us all together. Right? But anyway, this is a very biologically important aromatic system, right? So whenever we talk about purine rings, that's the kind of the basis here for that, right? Cool. All right. One more. We're good. All right, so this one, I got to cheat. And give me time. And you'll see why. Should just copy and paste stuff from the internet for you guys. Double that. I had this plan. Okay, you guys, please do not copy this down, because I will tell you exactly where you can look at it. I told you guys that too earlier. I said don't copy it down. Ugh, directions unclear. 1 out of 5. All right. All right. So this is what's known as a porphyrin. Porphyrins are everywhere in nature. Okay. Porphyrins are what make vitamin B12, right? They're the active site of vitamin B12. Cyanocobalamin is the fancy name for vitamin B12. That means there's a cobalt which sits right in the middle of this. It's also in your blood, right? Hemoglobin, right? So a heme unit is a porphyrin with an iron in the middle of it, okay? It's also found in chlorophyll, right? We basically have this plus a magnesium in the middle, right? So we see this system everywhere, okay? And this is a giant aromatic system, but only parts of it are aromatic, Okay, because if you go through and you count up every single lone pair and every single double bond, it's not going to come out to a Huckel number. But the inside of it is basically aromatic, and the outside isn't. Okay, so it gets a little bit trickier. Now, what you will notice is that this is a giant conjugated system, right? What color is chlorophyll? Green, and you have some of these other colors along the way too, right? What color is your blood? Red, right? So what color is vitamin B12? I don't know either, whatever. Maybe I was hoping you guys would know. I would have said yes. It's purple. Well, yeah. Okay. But anyway, these are highly colored systems is what it is, right? Especially when you add different metals in there. So these are actually really, really, really cool. And they've got a lot of interesting optical properties too. Right? If you guys take one of the biochem classes, or the he's probably talking about now, what's the pharmacology, not pharmaceutical chemistry. The pharmacology course that Dr. Barbosa has been teaching, right? You guys talk about the P450 enzymes, right? And they're basically the garbage men of the body, right? They just kind of react with everything and kind of detoxify a lot of things. And they work by having this at the middle of it also. So nature is fantastic at the synthesis of porphyrins, right? Very, very, very efficient. In real life, it's really tough to do, okay? We're getting better at it, and there's certain ways we can of improving it, but we're certainly not as efficient as nature is. So there's definitely something to be said about nature being an inspiration for chemistry, right? So anyway, I just wanted to kind of give a little bit of a flavor there for some of these very important biological systems that we see with aromaticity, right? Okay. I think that's all I needed to say about that stuff. What else?
Wait, Dr. H, you were talking earlier about like the different degrees of aromaticity.
Yeah.
So out of all these things, like which one's the better? Like.
I'll make you guys figure it out. How's that sound? No, what? I did. Listen to this. Man, please, I've got a plan, okay? No, that's a good question. I was literally this is literally the next thing I'm getting to, so. Yeah, go for it. Yeah. No, don't do my job for me. I'd hate to have free time in my life. Right. All right. So if we take this system here, right? Oh, I think I gave you guys the wrong name for something. It doesn't matter. You guys won't know. I'll correct it here in a second. I apologize. So if we have this guy here, which this is actually anthracene. The other one is phenanthrene. So sorry to disappoint you guys. I can tell from your stunned silence. Anyway, if we have this guy here, right? So we could go through and ask the litany of questions, right? And say, is this a ring system? Yes. Is this a Huckel number? Oh, what do we got? 2, 4, 6, 8, 10, 12, 14 again? Yeah, okay. So aromatic, and it's planar, and they don't talk to each other, and resonance structures, and blah, 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 right? All those things are true. Now, what do you notice about what I have here in terms of a reaction? Well, I've got bromine, and it's cold and dark, right? Are those reaction conditions that we're used to? Yes, right? That's something that we've done before. This is our halogenation reaction. And if we were in OChem 1, right? For an OChem 1, we would say, well, there's no reaction. This is an aromatic system. Well, as I've always told you guys, I just lie straight up all the time, right? Because what actually happens is this. We end up adding 2 bromines, nice, easy, no big deal, to those 2 specific carbons. Got it? You want to know what I'm about to ask you?
Well, I'm right there.
There you go. Let's figure it out real quick. through a sumo mechanism, right? Otherwise, we'd have to bridge in between both of those carbons, which, to be honest, isn't unreasonable necessarily. That could happen. It would be kind of challenging. Let's finish it up from there.
Of course.
That has the answers. Yeah, well, we're supposed to set a smart answer. Just take your table while you're trying to work, sounds good. Good. It's not too bad, right? Yeah.
Why does carbocation go to secondary instead of the bromine being added to the tertiary?
Why indeed? Right? Why indeed? A great question. How could we answer a question like that? Both of those might be true. What would the product look like if we just added the bromine to where that initial positive charge is? That's what I'm asking you guys, right? It's a great question. How do we answer a question of why doesn't it do something completely different from what it does, right? Right? So what was it? The question was, why am I drawing at an angle? Why isn't that a product?
Does it have like add to the opposite side?
Well, if we were going through the sumo mechanism, right? Yeah, if we're going through the sumo mechanism, yes. Yeah.
Because there's technically not a full positive on that carbon.
Nope, there is full carbocation. Yeah.
I don't know if this is right, but like, you know how like axial and like the electrons, like the placement, and how like some electrons take up more space than others, and like they like hit each other in a sense. You're looking at me like crazy.
That's in cyclohexane.
Okay.
Yeah. I'll give you guys a big hint. What chapter are we in? You rephrase the question. Oh, 16. The answer is 16, Diane. What's the topic of the chapter? Oh, okay. So what's probably going to be the answer here? Probably has something to do with aromaticity, right? And I said there's a big drive to generate aromatic rings. Yes? Take a look at the first product that we made. What do you notice about that first product? Hmm?
It's aesthetic, and like aromatic rings are kind of like equal in a sense, if you look at it.
So, there is a natural proclivity for humans to admire symmetrical things, right? In fact, that came out of a study when they said, you know, which person is more attractive. The more symmetric the face is, the more attractive somebody is, right? So, that's apparently, we know Taylor's kind here. She's very attracted to symmetrical aromatic rings. Right? Look, she's a woman who knows what she likes, right? That's nothing wrong with it, right? So, but there's another reason behind this, right? So I'm saying take a look at that one on the top, right, versus the one on the bottom. Tell me what the difference is. Yes?
The carbon where if the bromine was added where the carbocation is, it wouldn't, like, that wouldn't be like a usable, like it wouldn't fulfill the criteria for aromatics.
How many aromatic rings are on this product here? One, right? One, right? This here, right? Can all of these talk to each other? No, right? How many aromatic rings are here? Two nice benzene rings, right? Beautiful, symmetric, able to talk to each other. The only way we can get that is if we add the two bromines across those two carbons in the middle there, right? If you try and add your bromines to any of the other ones, you're not going to generate that nice aromatic set of systems there. Okay? Yes?
So if we check each of the two cyclohexanes for the Huckel number
Yep.
instead of the whole thing together. Okay.
Anytime you have a component of something that meets the criteria for aromaticity, then it is aromatic. That's kind of what I was trying to explain to you guys with this here. The entire thing isn't aromatic, just kind of the inside set of it, okay? But as soon as you hit that criteria, then thumbs up, you're aromatic, right? Here you have one aromatic ring, right? You have one aromatic ring and then just a set of conjugated pi bonds coming off of it. Got it? Do you guys see what I mean with this? Not all the pi bonds are in a ring. That's the difference. Do you guys catch what I'm saying with this? This is right? This is your ring. Ooh. This is your ring. Okay? The rest of this stuff is just conjugated pi bonds. Got it? Everything has to be within a ring. Good? I'm going to ask you guys the exact same question. You ready? Good days, happy days. Ugh. Well, you have it there, that's good. Nothing wrong with that. Hmm. Holy cow, didn't hide the name of this class. Right? Oh, looks like everyone's getting it. Yeah, I'm not gonna try to redraw that. Right? Why those two carbons at that particular place? It's pretty symmetric too. Is that a little appealing there for you? Oh, geez. Right? Right, but we react the double bond there that keeps the two rings aromatic, right? If you disrupt it, if you disrupt any of the other pi bonds, then you're going to break a level of that aromaticity, right? Do you guys get the point of what I'm trying to say? What do you guys need to start to look for when you're reacting aromatic rings? You keep the stuff aromatic and you try and make aromatic rings if you can. Got it? So when you're doing eliminations and you're forming alkenes and this kind of stuff, there's a drive to form and make aromatic rings. A pretty strong one. Okay? Good? All right. Story time, Dr. H. There's our good old buddy benzene. I put an alcohol coming off of it. This is our buddy phenol. Okay. A little bit of naming. Now, phenol, right, is the common name, right? You could call it something like what's a systematic name for this? Hydroxybenzene, probably something like that. Benzenol? No, I don't think it's that, right? Phenol is just the common name that this thing gets. Right? So if we have an alcohol coming off of a benzene ring, we call it a phenol or a phenol derivative. Okay? Now, you guys have probably heard about phenols quite a bit, right, in recent times. You guys remember hearing about BPAs? And plastics and stuff like that? You guys remember what BPA stands for? No Joe, I'm interested. No one else answers. Bisphenol A, right? So that's what bisphenol A looks like, BPA. Now you guys will know how to make BPA soon, okay? It's actually super duper duper easy to make. Guess what it takes? Acetone, phenol, and some acid. Sulfuric acid even. So cheap, cheap, and cheaper, okay? right? That's why they use it, right? When you're talking about making plastics like on the kilogram scale, right? You need stuff that costs fractions of a penny, right? So, easy to make. But there it is. So phenols, we see it in plastics, we see it in nylons, pesticides, pharmaceuticals. It's kind of everywhere, right? Antiseptics, it used to be used as an antiseptic also. But it's kind of not too good for you. So we've kind of moved away from there. There's our buddy benzene. We put a methyl group coming off of it. This is our buddy toluene. Okay? Very common solvent. We use it in the lab quite a bit. It's kind of a high boiling solvent. It's used in some markers, also as a solvent in like Sharpie type markers, that kind of thing. Now you guys have probably heard of toluene also, right? Of course we have. Because we've heard of something called TNT. What does TNT stand for? Nitrotoluene, right? So if we put some NO2 groups at certain positions, then we have trinitrotoluene, right? There's no invented TNT. No. Does anybody know? Good trivia questions. Nobel, right? Alfred Nobel. Right? He got upset because he saw the damage that it could cause, and so what did he make? Nobel Peace Prize, right? Got it? So, anyway, how easy is it to make TNT? It's honestly not that hard to do, right? It really isn't. And now, you know, we can, I don't know what it's, you know, recording, so I'm gonna get a knock on the door for guys in black suits or anything. You know? I mean, honestly, it's a really easy reaction to do, right? You know, the problem is not making it, the problem is handling it, right? So that kind of thing. But, you know, it's not so bad, to be honest. But toluene solvent and is kind of a precursor for a lot of other different applications in there too, right? Good. This is aniline. Aniline, I couldn't really find any good common uses for it, you know, that kind of might come up in everyday life. Remember, this was part of the or what was supposed to be benzocaine. Right, it was going to be an aniline derivative. It's used quite a bit for polymers and certain types of rubbers, that kind of thing. And it's also used to be old school rocket fuel, okay? So it doesn't burn all that well. It's actually a very common dye. The original butter yellow compound, which is actually what they used to make like margarine yellow color, was based off of aniline, but then that butter yellow compound, they found that it was going to be carcinogenic. So, well, not that it was going to be, it is, right? So they have to get rid of that, right? So aniline, whenever you got a amine coming off of the benzene ring. Okay. What else? Right. Now instead of an OH, we have an O-methoxy. This is anisole. Anisole has a very distinctive odor to it. And you guys might be even catching the hint in the name there, right? Anise, the seeds, right? Anise, the seeds there, right? It's a licorice flavoring, right? So this is a common flavoring agent or fragrance agent. Used also in some plastics and things like that too. Here's something that everybody's heard of. If you've got a double bond coming directly off of this, this is our buddy styrene. I can't spell all of a sudden. S-T-Y-R-E-N-E. Okay, do I even have to explain what styrene is used for? I think you guys got it, right? Polystyrene, right? It's just one of the first, or I should say first, excuse me, say one of the most common plastics, right? That's used. Also for styrofoam, right? What's the difference between polystyrene and styrofoam? Nothing, they just put a bunch of air in it, right? So one of them they trap a bunch of air, the other one they don't have air in there and it makes different plastics, right? That's all it is. Okay, this one here, we've seen this a billion times already. Benzoic acid, that's what this is. Everywhere, right? I mean, you name it, you can see benzoic acid in there, right? Remember, this is our precursor for acetyl salicylic acid, right? And that you guys used earlier in the semester, right? It's a precursor for different functional groups. Also, we'll learn how to make it. We'll learn how we can reduce it and oxidize and all these other kind of stuff with it, right? So a lot of different places where we end up with benzoic acid there. Let's see, what else do we want to talk about? Yeah, sure, why not? Now, instead of carboxylic acid, we have a ketone. This is our buddy acetophenone. Acetophenone. Very common building block for a lot of pharmaceutical compounds there. We're going to learn a lot about those ketones and how to react those, and this is just a common reagent that we have along the way. From what I read, it's apparently also part of the fake almond flavor. I don't know. Sounds reasonable to me. A lot of these things are kind of, we'll see them kind of show up in those kind of places, so there we go. Then we have this here. Now, this, right, is an aldehyde, and this is benzaldehyde. Oh my goodness, why can't I that's what benzaldehyde? Okay, there it is. It's a weird day. I'll put something in the water. I don't know. Benzaldehyde. Now, this is fake almond flavored. So when you go buy the stuff at the store, it's this. Okay. So you can see it's not too far away from acetophenone there, but it is distinct. This is also apparently used as bee repellent, right? So you guys ever seen the guys who they use that smoke to kind of calm the bees down before they go and catch the hives? Apparently they're kind of burning this is what it is. I had no idea. But now you guys know, and now you guys feel that your tuition check is worthwhile. I would never have figured this out on my own. I needed Dr. H.
There's gonna be an exam, so like, what's the best almond flavor?
That sounds like a good question. Just rote memorization that has no point to it. AKA trivia knowledge at the bar, right? No, the reason why I'm sharing this with you guys is because when we start to name things, or when you start to see things named in papers or, in other textbooks, these are the common names that you see for a lot of these, okay? We'll say things like, hey, this is a benzaldehyde derivative, which means, okay, you've got to look for your benzaldehyde, and there's some other stuff coming off it, that kind of thing in there, right? So these are common names that you see over and over and over and over and over and over and over again, right? These are not necessarily the IUPAC names, but, the other point of this is aromatics are freaking everywhere, okay? And you pretty much name a realm of chemistry or science and you'll see aromatics are kind of a part of that. But you guys already knew this, right? We've seen a lot of them over the last semester, and we'll talk about them now for the next 2 chapters, right? Cool. We got that. Yeah, what's up?
What is something a derivative or like actually something different?
You two, both of you guys, asking questions I'm about to get to. Very good, right? Let's talk a little bit about naming here, right? So there's my buddy phenol, okay? And now I put a nitro group on there, right? So as what we learned, or as we learned with naming of just simple alkanes, there's an order of importance for functional groups, right? And it just so happens that alcohols and most alcohol-containing functional groups are of higher importance than others, right? So we could call this 3-nitrophenol, right? So we start the numbering of the phenol, the OH, and we just count 1, 2, 3 from there to get to the nitro group. Got it? All right, so this is 1, 2, 3, so we could call this 3-nitrophenol. Good? Now, we don't want to do that because that's too easy. So what we're going to do is make it slightly more complex. So if we have some derivative, okay? If we have some derivative, it doesn't matter what that x is for our purposes. We assume that that x is the highest importance group. Got it? Okay, so for all purposes, it's highest importance group. The groups right next door to these are called ortho. Okay? Be meta. And directly across from it would be para. Or just abbreviated as P. So O, M, and P. Ortho, meta, and para. Remember, it's with respect to the X group, not the left and right or the up and down. You guys catch what I mean with that? I could take this and rotate it, right? And it's with respect to that X group, is where we define the ortho, meta, and para. So going back to my 3-nitrophenol, what would we call that? Well, our phenol is the highest importance, right? And so we could call that M-nitrophenol, right? Or meta-nitrophenol. Good? You guys with me on that one? That's all it is. So whenever you see that OM and P, it's just telling us what's the relationship between two different groups on the ring itself. Now, why this is going to be important is because later I'm going to come back and I'm going to talk to you guys about how we start to add multiple groups to the benzene ring. And some are going to be ortho-para substitutors and some are going to be meta-substitutors. Okay? So there's going to be ortho-directing groups, there's going to be meta-directing groups. All right, so that's where that terminology comes in. Okay? It's much easier than just doing the 1, 2, and 3. It abbreviates all that, right? So O, M, and P, that's all we really care about. Got it? Cool. All right, that seems like a good place to stop. So we will pick this back up on Wednesday. Yeah.
When do you want our quizzes back?
What do you guys want to have them by?
Friday?
Friday? Okay, I'll go back.